on with homework number 6. And this is problem 2. We have some more blocks, but now we have some pulleys involved with it as well. So block A weighs 100 pounds and is positioned on the slope, which is 25 degrees. And they're connected by pulleys and cables, and these are frictionless pulleys and they're massless pulleys, which just means that the tension everywhere in the pulley is going to be the same. And the coefficient of friction, kinetic friction, so we're going to assume the thing moves, is 0.15. So we want to find the weight of block B that's large enough to make block A accelerate up the slope at 5 feet per second squared. And then we also want to have figure out the weight of block B that's going to be low enough that block A accelerates down the slope. All right, so this is sort of like a variation on the same problem we did, but it's got a couple things in it. All right, so I'm going to go ahead and use my sketch right here for my, I'm just going to generically call this SA right there. So that's my SA for that length. And because this doesn't move right here, I'm going to go ahead and call this one right here. Here's going to be my SB. So I'm going to get this constraint out of the way. It's not going to matter that, we're going to pretend like it doesn't matter that this thing is diagonal. It's not really going to affect any of the thing, like it's that it's at a kind of an angle. It's fine. So looking at this right here, it appears to me that for the length of the cable, we're going to have 2 SAs, all right, and we're going to have 3 SBs. And if we take the derivative of them, we could say that we're going to have 2 VAs plus 3 VBs. Take the derivative of that again, and you have 2 AAs plus 3 ABs, right? Therefore, the acceleration of, let's say, A is equal to negative 3/2 acceleration of B. All right, so that's a constraint between these two. That's going to be true. I'm going to avoid working with the sign there, that negative, because I'm going to take all of the signs that really matter by the direction of motion. I know that things go up and down with each other, so I'm not going to play sign conventions here. I need an FBD of this and an FBD of that. All right. So one thing we have to be careful though, we might want to be lazy and just do like one set of FBDs for both parts A and part B, but I really think it'd be better to just redraw the thing out and pretend like we're starting fresh. Okay. So we take A, let's take the FBD of A, and it's a good idea to do that slope thing again. So we're going to make a slope like x prime and y prime coordinates. We're going to set that equal to an IBD. I didn't do a great job making a parallel line there on the bottom. There you go, a little bit better, not much. Okay, so on this side of the thing we have a normal force, Fn, and we have a friction force. Okay, so and the first one, this is just going to slide up, so the friction is going to come up, going to be going away from it right there. And I decide I'm going to call right here, I'm going to keep this pulley in there, and I'm going to go there and there. So I'm going to say 2 times Ft, the tension right there. And then let me see, I usually make that a dash line, don't I? And I'll have like this right here. This is going to be the weight of A. I didn't do MA G because we were given the weight, so we don't need to have like that. But we do need this guy right here, so we're going to have him, and he's going to be the mass of A times the acceleration of A. I think I will do B to the side over here, and then I'll do all the work underneath them. So do my FBD and IBD. In this case, we have an XY, and we will have free body diagram and inertial body diagram. And this guy right here, we will chop him up, and we're going to pretend like all three are directly upwards. So we're going to have 3 FT right there. So there's the tension in the rope, but where we've cut the ropes off so we can see inside. And then we're also going to have the weight of B. Now this thing is now going to accelerate downwards, so we're going to have the mass of B times the acceleration of B. And then that's all that belongs on over on that side. So let's do the find out what the normal force of this is going to be, and that's we probably might be able to, thinking about it, we might be able to just use the same that relationship for this part B of this problem, but I want to check on it. All right, so that's going to be the y prime direction, and I'll say the mass times the acceleration of y prime direction, but we know that's going to be 0. And so we take the forces, and I got to make this the angle right there. So I got the normal force is fully in the y prime direction, and the only thing I have left is I have a negative WA, and that's going to be cosine of theta, can be equal to 0. All right, so that's everything in the y prime direction. So Fn minus 100 times the cosine of 25 equals 0. So Fn is equal to 25 cosine 100, boom, is equal to 90.63 pounds. And now we want to have the friction force is going to be mu k Fn, or 0.15, 90.63. Yeah, so we go 0.15, boom. That's all of 13.59 pounds. All right, and so now we need to set up this in the x direction, x prime direction. Sum of the forces in the x prime direction equals mass times acceleration in the x prime direction. That right there. And so we got, oh, I forgot to write out my friction right there. There you go. Okay, so we have 2 times Ft right there. So that's going in the positive direction. I wanted to use something first. And then we're going to minus the friction. And then we're going to have minus WA times the sine of theta. It's going to be equal to mass times mass of A, I guess I'm doing this, times the acceleration of A. We'll come back to that in a second. No, okay, so let's just pause right there. I'll come over to this side. I'm going to say the sum of the forces in the y direction is equal to mass times acceleration in the y direction for this. So we get the weight of B. Oh, yeah, 3 Ft right there, right, is going to be minus WB, as all the forces on that side, equals mass of B times the acceleration of B. We know the acceleration of B in part A, right? So, but we don't know the weight, right? So that's something we're going to want to get. So we have 3 times Ft minus WB equals, now the mass of this thing is going to be the weight of B divided by 32.2, and now to the times the acceleration. And I meant to make this negative, right? This should have been negative. Whoops. Because this is the negative direction right there, right? So this should be a negative right there. So this acceleration is 5, right? Nope. I'm sorry. My bad. Maybe let's just do this up here. I'll do this up here. We could have said the acceleration of that. Actually, this would have made more sense up here. I'm sorry about that. We could have said the acceleration of B is equal to negative 2/3 the acceleration of A. And therefore, if the acceleration of B is just going to be 2/3 5. Oh, I meant to do this other one. So I'm saying absolute value. Maybe we'll absolute value of it times 5. So was that 10/3? So it should be, 10/3 should be 3.33333. And these are feet per second squared, right? So we could plug the value in here for 3.333. All right. So I'm going to set my Ft. All right, this is an unknown and an unknown, but I'm going to pull this over to the other side. So we're going to have, I think I'm going to be okay here, right, with the negative. So I'm going to have 1 minus 3.333 divided by 32.2 times WB. Is that going to be okay? Looks like I'm going to get a negative thing here, so I might have to pause my video and figure out what the hell I did wrong. Damn it. 3.333 32.2 divided. No, I'm okay. 1 minus. All right, yeah, that makes sense. Yeah. So that's just going to be Ft is equal to 0.8965 WB. Gotcha. All right, so we can put that into here. That's going to be, we're going to substitute that in. So say 2 times 0.8965. Oh, you know what? We could have done this. Let me just do this. This is probably the smarter way to approach it. It just occurred to me. Right? This is like one of those aha moments. We could find everything over here on the left-hand side that we had, and I should have just recognized that right away. But anyway, we'll not beat ourselves up here. All right, so we got the weight of A is going to be 100 pounds, and the sine of 25 degrees. Yeah, 25. It's almost time for me to go up to the class. I wonder if I could pause this video and it would stay all the way until end of class. We're going to experiment. We're going to see. Okay, and it's going to be equal to the mass, which is 100 divided by 32.2 times the acceleration, which we know is 5. So it's going upwards at 5, right? And so we're going to be able to get what the tension is in the cable. The tension required to pull this block up at that. So we take 100 divided by 32.2, multiplied by 5. Okay. Now we're going to bring this over to the side. So it's going to be 13.59. We're going to add it. We're going to take 100 and sine of 25 times, and we're going to add it. All right. So that's everything over on the right-hand side, and then we're going to divide it by 2. And we get 35.69 pounds. So over here, what we could do is we could say that WB is going to be equal to, I'll write it out, Ft over 0.8965 which is going to be 35.69 divided by 0.8965. So the weight of B, to be able to get this thing to move up there, I think I have it in the calculator. It's going to be 39.81 pounds. Okay, so I'm going to go to class now. I'm going to pause this and let's see if this video will keep until the end of class. I don't know. We'll see. I'm going to pause 15 minutes into the thing. We can hope. If it came back on. Yeah. So just got back from class. And we are doing part B now, right? So we got in part A, we wanted to figure out what it had to weigh in order for this to go upwards, up the slope at 5 meters per second, or feet per second squared, right? So now let's do the next part of it, part B, right there, right? So I'll make page 3, put my name in there. F21, this ES211, and this is homework 6. This is problem 2 continued. All right, so what we really want to do is do the FBD and IBD again, but this time with a different motion. So I'll have our FBD and IBD, X prime and Y prime, and we'll draw these things on here. Something like that. I'll make it the same. Cheating. Set them equal. We're still going to have this tension right here, so we're going to have 2 Ft, and the weight is still coming downwards this way. So that's going to be the weight of A, and theta are in here. We're still going to have the normal force, but now, because this thing is moving in that direction, the friction force is going in the opposite direction. So now you can compare those two to each other, this one versus that one. And we're also going to be coming this way down there. So it's going to be mass of A times acceleration of A. And I'll do this one over here again too. FBD, IBD, and I'll make a little block here. I guess this is the cylinder, isn't it? I guess I called it a cylinder. And this one has 3 tensions on it, right? So there's 3 Ft. We're going to set that equal to cylinder here in the inertial body diagram. But now this time it's accelerating in that direction, right? It's going to be accelerating up. So mass of B times acceleration of B. All right, so write the thing out again. Sum of the forces in the you know what, we can reuse, because nothing changed in the y prime direction, right? So we can use the same friction force. The friction force is going to be the same. It's just going to be in a different direction. So we could go ahead and just go to the x prime direction here. So sum of the forces in the x prime direction equals mass times acceleration in the x prime direction. X prime is positive in that direction right here. So we can say that we're going to have 2 Ft, but now it's going to be plus, because that's positive, FF right here. We're still going to have negative WA times the sine of theta, and I think that's everything on the left-hand side, and that's going to be equal to, now it's going to be negative mass of A times the acceleration of A. And I think we know everything over here, right? Is that what we said? Yes, we know everything over there, and we can figure out what the tension is going to be. So we'll say, I'll just leave it here as the force of the tension, plus R13.59 minus my 100 sine of 25 is equal to now negative 132.2 and times 5, right? So we could say that Ft is going to be, so let me double check here. So we have 100, hope it works out, right? Times 5, 32.2 divided, right? And yeah, I'm hoping. So that's going to come back over here, over to the other side. But it's going to be also additional 13.59. And now we have to have that 100 times 25, sine of 25 times, and that's going to be, come back over to there. Yep, that'll work out. Okay. And so then divided by 2. So it's 6.572 pounds. Now if we come over here, we get the sum of the forces in the y direction equals mass times acceleration in the y direction. And I forgot to put the weight onto here. WB. So we plug these in here. We'll go through there. We'll say 3FT minus WB is going to be equal to, now this is positive, WB. No, I just go MB. I'll go MB. MBAB, but positive. And so I can put the numbers in there. Say 3 times 6.572 minus WB equals WB over 32.2. Oh, I should have no, we already did the acceleration. We said that that was going to be 3.33333, right? 3.333. We can solve for WB now. So that's going to come back onto the other side, right? So it's going to be 3.333 divided by 32.2 plus 1. Right? And so we're going to multiply that by 3, and then we can divide those numbers out. And I think that's going to give us the answer, 17.87 pounds. Right? So our answers A is going to be WB is equal to 39.81 pounds, and B, WB is equal to 17.9 pounds. Ta-da! Now let's reflect on this a little bit. There's not a big, long, huge range in between, right? So WB, when it's light, is going to be, this is going to be sufficient so that this is going to go down 5 feet per second squared. When it's heavy enough, it's going to go up 5 feet per second squared. It's interesting. Okay. Well, that's all for this homework problem. 24.5 minutes long.